record. Alrighty then. So we're looking at 1996 question 4, back when AP Physics 1 was AP Physics B, and we're going to have a student is provided with a 12-volt battery of negligible internal resistance. You know, batteries can act like resistors themselves as the current flows through them. But we're going to imagine that there's no resistance inside this battery, and 4 resistors with the following resistances: 100 ohms, 30 ohms, 20 ohms, 10 ohms. The student also has plenty of wire of negligible resistance available to make connections as desired. So this is also magic wire that has no resistance at all. And then part A, using all of these components, all these pieces, draw a circuit diagram in which each resistor has non-zero current, so it has to have current. We can't do what they call short circuiting, flowing through it, but in which the current from the battery is as small as possible. And since electricity likes to take the path of least resistance, what they're secretly saying to you is, wire these 4 together so that the equivalent resistance, the Req that I've written there, is as high as possible. If you have higher resistance, you'll have less current running overall. And so the answer to this is to wire them in series, because series sums voltage drops and resistances, and we'll have the same current flowing everywhere. And so you're going to add these resistances together to get the largest resistance total if you wire them just all in series. And that would look like this. We'll draw a battery, long and short parallel lines, some wire here, and then just start putting them. We're going to do basically we're going to do one loop here, one series loop, and then just put the resistors in the loop around the way. So then let's just start drawing squiggly lines for the resistors. There's one, there's another one. Let's make a right angle. There's another one, and then come around here. Let's just put another one there and go back to the battery. And so then we got, we're going to number these. So let's designate them R1, R2, R3, and R4. And those will go with the ohms as they've listed them from highest resistance to lowest resistance, from the 100 ohms down to the 10 ohms. And so then there's going to be the 100 ohm here, the 30 ohm here, the 20 ohm here, and the 10 ohm there. And then those would be R1, R2, R3, and R4, just for labeling purposes. So that's the answer. You're done with that part, but let's explore it a little bit more in case we want to practice doing VIR charts with this. So let's do a little VIR chart here. So Jasmine, you're my physicist of the day. What would be your favorite color for me to use here? Back? Sounds good. Let's do that. So we're going to draw a VIR chart. La la la. Yep. 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 And because it's a VIR chart, write V equals I times R across the top. And then we're going to make it a VIRP chart. Put a P in a separate column on the far right so we can do a little bit extra stuff with this. And then make a row for each resistor and a row for the totals. So we'll have R1's row, R2, R3, and R4, and then a row for the totals here. Totals. And then just make lines for your rows. And then make a column for each variable, for a column for your voltages, or your voltage drops, a column for your currents, and then we have a column for the resistances, and a column for the power on the far right. We'll deal with the power once we're all done with the VI and R part. Now let's fill in what we have, what we call the givens. Well, first of all, they tell us that we have a total EMF, or electromotive force, which you write in epsilon to signify, of 12 volts from the battery. And that goes in your totals voltage part. So we're going to have 12 volts in our VIR chart. And then they give us each resistor's resistance. And so let's just fill that in the R column. So we have 100 ohms, 30 ohms for R2, 20 ohms for R3, and 10 ohms for R4. Now, because series adds together resistances, we can get our total resistance just by adding all 4 of these together. And that's why we wired them in series. So we get the highest resistance possible and get the least amount of current possible. So the total resistance is going to be 100 plus 30 plus 20, that's 150, plus 10 more, that's 160 ohms. And now that we have the 12 volts and the 160 ohms in the totals row, we can use VIR to solve for the total current. So we can actually find out, they didn't ask us how much current would flow, but we can find out how much current we're going to have here. Yeah, Jasmine. How do I know it's series? Well, series means that the resistors are wired so they're in one loop together, and there's only one path for the electricity. So you can think of like S for series, S for single, single what? Single path for electricity. And so the electricity would have to flow, and let's do the current here in a light blue. The current then would have to come out of the positive side of the battery, run through this 100 ohm, through this 30 ohm, through this 20 ohm, and through this 10 ohm, and then back to the battery. And that would be your I plus your conventional current, the flow of positive charge. And there's only one way for it to go. So whatever flowed out of the battery has to go through each resistor and then back into the negative end of the battery. And so the total current is going to be the same current everywhere. And that's how you know that it's in series. When you look at, and there's no junctions to branch out and to split. And if it splits, then you have parallel pieces, or parallel branches, as we say. All right, well, let's find that total current. And to do that, we would do the 12 volts divided by 160 ohms. So getting my trusty calculator here, 12 divided by 160 is 0.075. 0.075. And what are the units for that current? Amperes. Good job, Andrew. A capital A for amperes. Now, as we just established, when we're in series, you have the same current everywhere. There's no opportunity for the current to branch off and split. So the same current is flowing through each resistor. And so in each resistor's row, we can just go ahead and fill in that 0.075 amps. 0.075 would have to flow through out of the battery, so it's in the total. Then 0.075 amps of electrical water or electrical current would have to flow through the 100 ohm. And then after flowing through the 100 ohm and dropping some energy, it'll have to flow through the 30 ohm and drop some more energy. And then it'll flow through the 20 ohm and drop some more energy. And then it'll flow through the 10 ohm. And then it'll go into the battery and flow through the battery and keep on going around and around. Now that we've collected the I and the R, two variables in each row, we can use VIR to calculate the voltage drops that are going to happen in each of the resistors. Tarek, what color would you like me to use for voltage drops? Green. I love it. All right, so here we're going to use voltage drops. So the voltage drop across the first resistor is going to be 0.075 times 100. So we'll just move the decimal over twice, and we'll get 7.5. And what are the units for voltage drops, for potential differences? Yeah, just volts. So we'll have a capital V there for volts. And then 0.075 times 30, 2.25 volts. And then 0.075 times 20, 1.5 volts. And 0.075 times 10, we just move the decimal, so we get 0.75. Now, series adds voltage drops and resistances and has the same current everywhere. So since series adds voltage drops, we should be able to double check our work here and add together all of those voltages, and they should add up to 12. And so if you check that, you'll find that those 4 green voltage drops do add to 12. Now let's kind of color what's going on here. So you have your colored pencils today. And you're going to get out 1, 2, 3, 4, 5 colors. So if you have all 5 of your colors, and we're going to color warm to cool colors. So I'm going to start with red highlighter, red colored pencil. And we're going to follow the current, and we're going to track its energy levels with warm to cool colors, so that every time it drops some energy, it has a voltage drop, we'll change the color a little bit cooler, a little bit colder, to show that it's the same current, but it's kind of cooling off as far as the energy it has from the battery, the joules per coulomb. And so we start at the positive side of the battery, and we start as warm as possible. So I've got my red there. And then we're going to stay red until you drop energy across your first resistor. And so this is representing that the current running is carrying, at that point, it's carrying 12 volts. Or you could imagine that it's carrying 12 joules of energy per coulomb of charge that's flowing. But then, as it crosses over, as it takes the bridge over R1, it converts some of those joules of electrical energy into heat and light. If R1 is a light bulb, then it's converting energy into heat and light. And so how much energy is given off is represented by the voltage drop. And we just calculated that it's going to drop 7.5 volts. So the voltage drop, the delta V1, is equal to a negative 7.5 volts. And I put the negative to represent that we're going to subtract off 7.5 volts from our 12 volts. And so it's going to lose 7.5 out of 12. So how much does it have left if you subtract out 12 minus 7.5? Yeah, so good job, Michael. We'll be down to 4.5. And so I'm going to color a little bit colder. So think Roy G. Biv, go red, you could go orange or yellow. I'm going yellow. And so in this yellow area on my circuit, it's got positive 4.5 volts of voltage left, or potential left. Positive 4.5 volts. And now we're going to run into this 30 ohm resistor, and as we kind of bridge over that, we're going to experience another voltage drop. That resistor could be a light bulb. It could convert some of our energy into heat and light, and so that's represented by a change in voltage, and this is number 2, and we calculated that's going to be 2.25. So we're going to subtract 2.25 volts from our 4.5. And just by coincidence, when you subtract 2.25 from 4.5, you end up with 2.25. And so pick a cooler color. So go Roy G. Biv, maybe G. So I'm going to go green now. And so now at this green is representing that my potential is at a positive 2.25 volts. And then we're going to make another voltage drop across R3 here. And we calculated we're going to lose 1.5 volts. So that's our delta V3. And we're going to cool the color off a little bit more. I'll cool down to blue. And so now at this blue color, what are you left with now? You had positive 2.25 going in. You lost 1.5. What are you down to? You're down to 0.75 volts, which is perfect because as we cool off one last time and go down to maybe purple from blue and run all the way back to the battery, Kirchhoff's loop rule says that as you make a loop, as that blue I plus loops around, every time it loops around, it has to use up all of the energy in the charge that it got from the battery. And so it has to drop, if you have 12 volts loaded in from the battery, it has to drop all 12 to obey the law of conservation of energy. And so we have to come back in this purple, we have to come back at 0 volts to get into the, as we coming to the negative side of the battery. And so this last drop, beep, delta V4, has to be a negative 0.75 volts. And when we look at the VIR chart, we see that that is exactly what we calculated it to be. And so that's perfect. We obeyed Kirchhoff's loop rule by dropping all of the voltage around the loop. And it connected with our VIR chart, and we didn't even use Kirchhoff's loop rule, at least not out loud, as we were filling out our VIR chart. So there's a lot of really cool back checking that happens in circuits when you use all of your equations and things that are available to you. Now let's do one last thing with this. Let's rank as these are light bulbs, let's rank them in terms of brightest to dimmest. And that's going to be connected with which variable, which their brightness is directly connected to what? Yeah, good job, Anthony and Patrick. So power. So that's why I left that power column alone till right now. Let's go ahead and attack that power. And Jasmine, what color do you want me to use for the power values? Yellow? All right, let's try yellow. I'm going to try a slightly darker yellow. Maybe it'll show better for you. Okay, so power, and if we use Ohm's law VIR for the voltage, we can use Joule's law, PIV, P equals I times V, for the power. And so now we have the I's and the V's, and we'll just pull them and just multiply them for each row. So the first power for R1 is going to be 7.5 volts with 0.075 amps of current flowing. And so 0.075 times 7.5 is 0.56. And then there's a 2.5 there, but I'm just going to end it there and write a W for watts the unit for power? Yes. Yes. Watts the unit for power? Yes. Wait, what's the unit for power? Yes. Watts is the unit for power. Now we have 2.25 for the next one times 0.075, and that's going to be 0.16875. I'm going to round that to 0.17 watts. And then I have 1.5 times 0.075, and that's going to be 0.1125. I'm going to round that to 0.11 watts. And then I have 0.75 times 0.075, and that's going to be 0.05625, and we're going to round that to 0.56 watts. Now to get the total power that's dissipating from all of the light bulbs, you always just add those powers together. It doesn't matter how you wired them together. For power, once you've taken into account the series and parallel rules in getting your V, I's, and R's, then you just add these all together. So we're going to add together all four of the powers dissipating to find out the total power dissipating from the circuit, 0.56 plus 0.17 plus 0.11 plus 0.056, and we get 0.896 watts. And if I want to follow my rules from before, I could round it to 0.90 watts, but we'll just leave it there. That's fine. Now, let's rank them. Who's the brightest? Maybe we'll write underneath here where we have some room. Brightest to dimmest. Shoom. And so we'll put like greater than signs to represent who's brighter or dimmer, or who has the most brightness. So R1 at 0.56 is going to be the brightest. So R1 is brighter than R2, is brighter than R3, is brighter than R4. All right, so we've successfully worked out series circuits. Let's take a look at parallel circuits.